Today we have lecture number 5, the second lecture of this week, and we will continue the application of Navier's equation. We will solve a problem, we call it a Couette flow problem, in which one of the plate would be fixed and other plate would be a moving plate. In the previous problem we have done both plates fixed. Let's first see this content. We will once again see the physical meaning of the Navier's equation, which is very important, and in all the courses, it is very important to understand the meaning of that equation. And then we will talk about the assumption which we have we usually encounter in most of the fluid flow problem is fully developed flow, and the same assumption is used in heat transfer problem as well. And then we will talk about this particular problem we will solve using the same way as we have solved the earlier problem. The problem here is also steady state laminar flow, but here one of the plate would be fixed and one of the plate would be moving. So we call that problem to be as Couette flow problem, because the Couette was the person who actually solved that Navier's equation for that particular problem. So in his honor, such a flow is usually called as Couette flow. And then we will see in short the applications that is actually common in the journal bearings, where we can use this result to get information of the velocity profile. Okay, let's start with the continuity equations, and as you see, divergence of the velocity vector is 0, so that is actually the continuity equation in vector form, and it is very important to know because we have already derived in previous lectures. So one of the reason for deriving the fundamental deriving the equations using the fundamental principle is we better understand the meaning of such equations, what actually this equation is telling us. In later part of the course, we also come again to explore the meaning of this divergence of velocity. So far what we have learned is actually it is depicting the fact that the fluid coming to a certain region of interest, so the rate of change of their mass flow would be depending on how much is coming in and how much is leaving. So if there is a no source term or no mass is creating in the region of interest, so their divergence of velocity would be 0. So it means there is no source term or even no sink term. So and we know while deriving this equation we have what the assumptions we have taken. If you recall, one of the assumption was density is constant, and we call it an incompressible fluid flow. So in this course most of our discussion would be incompressible fluid flow. So we will not talk about where the density is varying or density is not constant. So such a study is called compressible fluid flow or gas dynamics, because gases are considered as compressible. So that is a full-fledged subject of gas dynamics, which is out of our scope right now. So when we write in the vector form, the advantage of writing down such equations, one more assumption we have taken in deriving this is the fluid is assumed as Newtonian fluids, and their viscosity is constant. So the density is constant, the velocity is constant, so we can say their fluid properties are constant. So that is what is actually clear from this equation. So whenever we are writing down the equation, we have to understand what actually it means. Secondly, as you have written this vector form, so when you write in the vector form, the advantage is the equation becomes independent of the coordinate system. So you, by having the definition of this del operator, which is a vector actually, as you know, the vector and take the dot product of the vector and the resultant is a scalar. So such a product is called a scalar product. So this is the divergence of velocity, and it is written in the vector form, and this vector form means it is you can write for any coordinate system. So here I have written it in this Cartesian coordinate system. In the Cartesian coordinate system, u, v and w are the velocity components. It is actually physically it is depicting the same fact that the mass is conserved. So within the region of interest, whatever is coming in and whatever is leaving, so the rate of change of the mass within this fixed region of interest is depending on what is coming into this region and what is leaving the region. So because whatever is coming, that would leave. So there is no creation taking place within the region, or there is no sinking takes place within the region. So that is actually so far the physical meaning of this continuity equation. And after completing this Reynolds transfer theorem, when we will derive it using the integral approach, because so far we have derived it using the differential approach. So in the integral approach, we have another aspect of the same physical principle. So basically the genesis of or the origin of this equation is a simple fundamental principle, that is the principle of conservation of mass. So I hope that you better understand the equation, you can express it in its words, as well as you know what are the underlying assumptions while deriving such equations. Okay, let's go to this momentum equation in vector form. So we know this vector form means this term is an inertial term, this term is a gravitational force or a body force, the only body force that is acting so far, and this is the pressure gradient, and this is the viscous part, which is a second order part of this del operator. So it's a non-linear term here. So we better understand this physical meaning of this material derivative. This is a rate of change of velocity, which is actually the rho times an acceleration. So it is rho times acceleration, this is rho time acceleration. So the units for a given equation must be same on either side. If it is a correct equation, at least it must be dimensionally consistent. So you see it is rho times acceleration, but you know that this is not just a local acceleration, but having a local part of the velocity change as well as the convective part of the velocity change. So if you write in the expanded form in Cartesian coordinate system, okay, by the way, the same is true if you write momentum equation in vector form. So here it is independent of the coordinate system. You can write it for Cartesian, you can write it for cylindrical coordinate system, and you can write it for spherical coordinate system. So depending upon the problem at hand, we can use the governing equation to solve the problem. So most of the time, I mean, we will encounter the Cartesian form of this equation. As you see, once you write in an expanded form, you can see this local variation of velocity, which is the so-called instantaneous change in velocity. So velocity is changing with the time. So actually, if the fluid is accelerating, which is actually the instantaneous velocity, and you know here the fluid is changing its velocity as it is moving in x, y and z direction, and once it is moving, the velocity vectors are u, v and w. So this is the convective part of the acceleration, and rho times acceleration is the force per unit volume, which we already know that is actually representing the whole terms are on the left hand side are the inertial term. On the right hand side we have the gravitational term, we have the pressure term, and we have the viscous term. So right now we have three unknowns, u, v and w, and your independent variables are x, y and z, which is representing a space, and t is a variable which is representing a time. So we know how we have derived such equation, and we know the underlying assumptions. So one of the assumption is constant density, another assumption is constant viscosity, and here we have only included one of the body force, that is the gravitational force. It means we have disregarded, or we have not taken into account other body forces like electrical fields, magnetic fields, electromagnetic fields, or the fields which are generated due to the motion of the earth, motion of the earth around its own axis, as well as motion of the earth around sun, as well as the motion due to the rotation of the moon. So all these, all type of other body forces which act from a distance have been ignored. So only the body force that is included is the gravitational force. Another assumption we have actually taken is, well, we are talking about viscous term. So we have used the Stokes hypothesis, which relates the shear stress which is acting onto the fluid element in terms of the velocity gradients. So we have used the constitutive relation or auxiliary relation, or in short, this equation is applicable for Newtonian fluids, which follow a behavior in which the shear stress would be directly proportional to the shear strain or the velocity gradients. So it is very important to understand the physical meaning of each term, what each term is all about, as well as the underlying assumptions. So this is what I expect from students. They have an ability to express equation in their own words, as well as they understand the limitations, they understand the underlying assumptions. So this would be true not for these equations, and this would be true for every equation you will encounter in the course. And the reasons for deriving such equation is to understand the physical meaning. That is the most important thing. Otherwise, these equations would be just a mathematical representations, and you won't be able to appreciate how such equations are useful. So unless and until you understand how actually they have come from where they have come from, and what are those assumptions under which they are applicable. So this is very important point. I have already explained it in the previous lecture, as well as I will explain in the future lectures as well. So I mean, this is one of the learning outcome which we expect from this course. Okay, now let's start with Couette flow. So as you see earlier, we have applied the Navier equation to solve such a problem in which two plates were fixed, and they are infinitely long, and there is only dominant flow in x direction, and there is a typical parabolic velocity profile. So maximum velocity in the middle layer, and the velocity at the edges due to the no slip boundary condition is 0. So this is what we have already worked out in the previous problem. Okay, now what we have done is we have the same two fixed plates, but the thing is the bottom plate is fixed, but at this time the top plate is moving. So what we expect is the layer which is in direct contact with the top plate would be moving with the same velocity as the velocity of the top plate is, and here in this case u0 is the velocity of the top plate. So what actually has changed, the velocity distribution would not be the same as the previous case. So velocity distribution has changed, and we will be able to calculate the mathematical expression today in this lecture what mathematical equation represents this velocity variation, which is actually taking place in this y direction, like the same as the previous problem. So such a problem was studied by Couette in 1858 to 1943. I mean, that's why such a flow is called Couette flow. So we are assuming it a steady state problem because we are not interested in the variation of the time. So secondly, we are not interested in the z direction. So it's a two-dimensional flow, and we are assuming a constant density. So it's an incompressible flow, and we are assuming the fluid is observing the Newton's law of viscosity, or the fluid is Newtonian fluid, where stress would be directly proportional to strain rate, or you have stress and strain have a straight line behavior. So this is the assumption, and the schematic of the problem looks like this. The bottom plate is fixed, and which is not moving, is stationary, while the top plate is moving, and the width or the distance between the two plates is we represent by a symbol B, and the top plate is moving with a constant speed. I mean, and we use a letter U not to represent the constant speed. So one of the plate is fixed, other is moving. What we are actually interested in, like the same for the previous problem, we will be interested in the velocity profile. Here also we are interested in how the velocity variations taking place. I mean, not all layers of the fluid would be moving with the same speed, but there would be certain velocity distribution. So different layers of the fluid would be moving with different speed. And obviously at this point we will assume, we will take an assumption, because as you know, Navier's equation is having a lot of terms, and by taking those assumptions we are in a position to get rid of several of the terms of the Navier's equations, and you end up with few terms, and these few terms can be solved mathematically. So now we will look at this, what is meant by this fully developed flow. So as you know, let's say you have two plates. The top plate is in motion with the speed u naught. At a given location there is a certain velocity profile, or what you call it, this is an upstream side, this is in a downstream side. So the direction of the flow is from upstream to downstream. And as you know, obviously how this is possible, it is only possible on this upstream side you have some higher pressure, and on the downstream side you have some low pressure. So this difference of pressure forces the fluid to move in this direction. So if pressure is higher here, lower here, then the fluid will be moving in the opposite direction. So what does it, the fully developed flow means? As you are moving from upstream to downstream, so if your velocity profile is no more changing, when x is x1, your location is x1, and as you move in the direction of x to some other distance x2, your velocity profile remains the same, it doesn't change, then you call that such a flow to be fully developed. So it means once the flow enters into this channel, its flow is not developed. After traveling certain distance, the flow becomes developed, and once say it is fully developed, it means its velocity profile is no more changing as you are moving in the x direction, or in this traveling from upstream to downstream. This fully developed flow is present not just in this two fixed plate flow, between the fluid flow between two fixed plates, or between one fixed and one moving plate, but even in the pipe cross sections. So how do you know that this is a pipe cross section? As you know, this is a center line. This line is a center line. So it means the cross section is not two plates, but cross section is circular. So it is a pipe flow. So what actually the velocity profile when flow enters into the pipe is uniform. So every layer of the fluid would be moving with the same speed. At this cross section, all the layers of the fluid which is moving into this pipe, entering into this pipe, would be having same velocity. Okay, what happens is, we will talk about later the concept of boundary layer, and due to the viscous effect, what happens is some of the layers got retarded or their speed is reduced, and some layers would be moving with higher speed. So there is a velocity distribution as it enters into the pipe. So this velocity profile you see is a different profile after moving from this distance to this distance. The velocity profile has changed. Initially it was uniform, and then it has this profile, and then it is this profile. After a certain distance, it has developed a profile which is no more changing as you are moving. So that region would be called as fully developed region, or the flow is called fully developed flow. So whereas in the entrance region, what you call it, the fluid has not fully developed, it means the velocity profile is changing. We call it entrance region. So if you have a very long pipe or a long channel, so at some distance, usually 10 times of the diameter, if let's say diameter of the pipe is d, so after 10d distance approximately, the flow becomes fully developed, depending upon the Reynolds number of the flow. So this is what the concept of fully developed flow. The velocity profile no more a function of x. So at any value of x, the velocity profile remains same. And keep in mind the velocity profile is changing with y, because when y is let's say here in this case it's a pipe, so it's a radius. So when you're at the center of the pipe, you have a maximum velocity, a core velocity. Whereas you are at the edges or the walls of the pipe, the velocity is 0. So the velocity is varying in this r direction, radial direction, but the velocity is no more varying in the downstream direction or in this direction of x. So such a flow is called as fully developed flow. So this assumption is very useful because it disregards what is actually, because it is very useful in very long channels, because in long channels at the entrance region flow gets is developing, and once after traveling certain distance it becomes fully developed. So its profile is no more changing. So as we already have seen, if velocity profile is not changing, it means the volume flow rate will not be changing. So the properties of the fluid flow in that long channel remains the same. So that is one of the advantage. Okay, let's solve it mathematically. So the first step in solving any problem is first of all write down the governing equations. Since we have already taken the 2D assumption, so we have not talked about the variation of the W component of velocity with respect to Z. So this is the continuity equation in 2 dimensions, and we already know is a steady state problem, so there is no time dependent term of this inertial term, have no time dependent term. Secondly, which is not mentioned here, but if you see the gravitational force in x is not there, but the gravitational force in y is there. So we have 2 momentum equation, one in x, one in y. Why we don't have it in z? Because it's a 2D problem. Similarly, in continuity equation we have a simpler version. So once you write down initially, that's a 2D problem, so you can write the 2D governing equations. So you have complete Navier Stokes equation in 2D. With an assumption of constant density and constant viscosity, and you know where the mu has gone. Actually, as you know, the density usually term is here. So if you bring density here on this side, so mu over density would be called as kinematic viscosity, and we have already seen in this previous I believe the first lecture, the kinematic viscosity is the dynamic viscosity divided by the density. So I mean, in different ways you can write down your governing equation. So this is one of the way Earlier in the earlier problem, I have written the whole governing equations in 3 dimensions, and then by employing the assumptions, we have reduced it into a simpler form. Okay. So first and the foremost important assumption here is the fully developed. It means the velocity profile is no more changing with the velocity component in x is no more changing as you are moving in the x direction. So u becomes an independent of x. So that would be an important assumption. So we will be able to get rid of this term dou u by dou x, which would be 0. So and similarly, if you will make this 0, so you only end up with this term in continuity equation. Okay, let's see by employing the assumption of fully developed flow in continuity equation, first equation. So this term is 0, so what you end up with? You end up with only this term. So since velocity is no more changing with x, and we have written a partial derivative, it means velocity would be some function of x and y. Why not z? Because it's a 2D problem. So velocity here is a function of more than one independent variable. It could be x and y. But once we employ this assumption of fully developed flow, it means velocity is no more varying with x, no more varying with x. But and once you employ this assumption here, what you end up with? You end up with this equation. So further, you learned that the velocity component in y is no more changing with y as well. So it means the y component of the velocity, which is some function of y, is constant, because if you take the derivative of that component, derivative of constant is 0. So it means the velocity here becomes constant here. For this bottom plate, as you know, the layer of the fluid which is in direct contact with this bottom plate is stationary. So when y is 0, or even y is b, the layer which is moving, the top layer, which is moving with velocity y naught, but the y component of the velocity would be 0. It means there is no flow taking place in the y direction, either here or here. So fluid is not coming out of the plate. That's why v is 0 when y is 0 as well as y equals to b. So this boundary condition is called as no slip boundary condition. So if we employ this, we have this boundary condition. Okay, so what we learned from this no slip boundary condition is that when y is 0, you are here, so there is a velocity component in u, obviously, which is also 0, but since this plate is stationary, and the u component of the velocity is u naught, but the y component of the velocity is 0, because of the fact that there is no fluid coming out of this plate, and the same is true on this moving plate as well. So what we conclude here is the velocity component in x, which is a function of y, is non-zero. It means there is a velocity variation taking place in y direction for an x component of the velocity. Y component is 0 here at the bottom plate as well as the top plate. So if you look at the y momentum equation here, you see that the u has v is 0. So in the y direction, this v is 0, this v is 0, this v is 0, this v is 0. So your y momentum equation having whole thing is gone on the left hand side. So you only end up with this pressure term and the gravitation term. So your momentum equation, y momentum equation, reduces to 0 here, and the viscous terms are gone. Only you end up with the pressure term and the acceleration due to gravity term. So as you know, it is rho g, but once you divide by rho, so rho and rho cancel out, so you only end up with g here. So this would be simplified by taking an assumption that the velocity component of y is 0. So you end up with this simplified y momentum equation. Or you can write like this, bringing onto the other side because it's a negative. So if you go onto the left hand side, it becomes positive. At this point, you know that the pressure is varying with y. So if you multiply rho with g and you integrate, you know, since it's a partial derivative, so pressure would be a function of more than one variable, and as you know, it's a 2D problem, so pressure would be some function of x and y. And how it varies with y is given by this equation. So if you integrate this, you would get this because rho is this multiplier, and the constant would be some function of x because pressure is a function of y, so constant would be some function of x. If you differentiate this expression with respect to x, so if you differentiate with respect to x, g is constant, rho is constant. Since we are differentiating with respect to x, so y is assumed constant. So the derivative of the constant would be 0, which we have not written here. And here we can write rho, which is a constant. So whatever the function is would be changing with x. So this is just a differentiation of this expression. So if you integrate, you are going to get the same equation back, because you know derivative and integration is nothing an antiderivative. Okay, let's see the x momentum equation. In x momentum equation, you know that dava u by dava x would be 0 because of this so-called first of all the v is 0 because whether it's an x momentum or whether it's a y momentum, your v component is 0. So v is 0 here, so you get rid of this term, but it is u because it's an x momentum equation. The next assumption is we know that they're fully developed, so we get rid of this term also because velocity is no more varying with the x, so its second derivative would also be insignificant. So the whole left hand side would be 0, and you end up with this pressure term and one of the viscous terms. So it's a kinematic viscosity, which is mu over rho, and this is the second order term of the velocity variation with respect to y, second order term. As you see here, you can write this way as well. Okay, we have rearranged this equation in such a manner so that we can integrate it to get the velocity profile, because this is an objective for solving the equation is to get the velocity profile. I have rewritten this term onto the left hand side and this term onto the right hand side because this rho and rho cancels out, so you only end up with this mu will be on this denominator of the left hand side. So that is what has come here. What this equation, as we already know that the velocity component in x would be some function of y. So velocity is a function of y, so velocity is changing as you are moving in the y direction. So this term would be, if you integrate this, since velocity is only a function of y, is not a function of x, so this partial derivative of second order has come into an ordinary differential because only one independent variable, that is y, is here. So that makes our life mathematically simpler by turning equation into this partial differential form into ordinary differential form, even though it's a non-linear term, second order term, but still we have one independent variable, so we have reduced the vigor of this equation. Secondly, if you have to integrate this, so second derivative would turn into a first derivative, and if you integrate with respect to y, you are going to get y and some constant of integration. I have used the letter a to represent the constant of integration, and obviously we have to integrate further once again in order to get the velocity profile. So you got the expression for the velocity profile, which is some function of y. y square and y, and as we have done it in C1 and C2 were the two constants, so here we have constant a and b. And you know how to get a and b? The way we have used in the previous problem, by employing the boundary conditions. So once you employ the boundary conditions, you will be able to get information about a and b. So as a first boundary condition, when y is 0, you know the velocity component in x direction is also 0, because it's a stationary plate and the layer which is sticking to this stationary plate is also stationary in the x direction. It is already, there is no velocity in the y direction, but the velocity in the x direction is also 0. So once you put 0 here and y 0 here, y 0 here, so you got rid of this term. So what is end up with? B equal to 0. So this is you got b equal to 0 by employing this boundary condition. And another boundary condition is when y equals to b, you are at the top plate. So at this point the layer velocity would be the same as the velocity of the top plate. So velocity of that layer would be when y equals to b. Actually here y should be b, not uy, because y is b, and here, so this velocity component would be equal to the, because you can substitute y equals to b here. So it would be the u naught here. Okay, so is here you have u naught and y would be equal to b. So b square and b a times b you are going to get. And b we already know is 0 from this first boundary condition. So u becomes u naught, y becomes b. So here y is also b. So we only thing the unknown for the constant here is a. So a you can work out in terms of all other parameters. Okay, so we have the knowledge of both a and b. So the next thing is so simple that you have to substitute a and b back into that equation. So eventually what you got it? You got the expression for the velocity profile. So this is the variation of the u component of the velocity, which is only dominant component of the velocity, which is a function of y. So if you look back to our boundary condition, because this is the solution you got. So when y is 0, you are here. So once y is 0, so this is a multiplier for this whole term in this square bracket. So whatever the term is u naught, whatever the term in the square bracket, you eventually get the velocity would be 0. That is the no slip boundary condition. Similarly, if you substitute y equals to b, so you put b and b would be 1, and 1 minus 1 would be 0. So this term, whole term is 0, 1 minus 0, and y is b and b is 1. 1 multiplied by u naught would be u naught. So your boundary condition, second boundary condition is also satisfied. Then when y is b, then your velocity is equal to u naught. So you need to make this your habit. Whenever you solve something, you got certain equation, you must have to check whether it is satisfying your boundary condition. So in most of the fluid flow problem, if you solve some equations, you get certain results. So you must have to check whether your results are meaningful to the boundary condition which you have employed in order to get the result. At least it must be valid. If it is not valid, it means there is something wrong with your solution. So this is as a rule, you have to use this. Whenever you come up with a solution, you always check that whether it is satisfying the boundary condition and make it your habit. Okay, we can write in terms of non-dimensional form, because as you know, y over b, y is in meters, b is in meters. So meter and meter would be dimensionless. So just I brought u naught in the denominator. So here, instead of getting velocity, you got the ratio of the velocity. So it is meter per second, it is meters per second. So this equation would be in the dimensionless form. So in later part of the course, you will learn that dimensionless forms are useful. I mean, here it is not that so useful, because this velocity profile or the ratio of the velocity is some function of the velocity of the plate by which the top plate is moving, as well as the pressure gradient, and this ratio is a function of a dimensionless distance, not the distance but a dimensionless distance. So dimensionless distance means y over b ratio. Okay, for simplicity, because this is a multiplier, minus b square 2 mu u naught dava p, the whole thing I have assumed as p. So this velocity profile looks like 1 plus p times 1 minus y over b over y over p. So this would be much simpler form of the equation, which represents the velocity variation takes place in this y direction. So what we learned is if your velocity, magnitude of the velocity is depending on this parameter p, and this parameter p is depending on the width between the two plates b, the velocity of the top plate, and the pressure gradient that is present in the x direction. So more the pressure gradient, more will the value of p. Okay, let's see its solution just by assuming it. And what I do is I plot different values of p. So first value of p would be 0, and how it is possible to have 0? Only when pressure gradient is 0. So dava p by dava x is 0. So you get different velocity profiles. For example, this is a straight line profile because velocity here is 0. So on this axis I have not velocity but the dimensionless velocity, and on the y axis we do not have a distance b but we have a dimensionless distance y over b. So when y is 0 you are here, when y equals to b you are here, because when y equals to b this ratio would be 1, and here the velocity ratio is 0, so it means the velocity is 0 here, and here the velocity is ratio is 1, it means your velocity is u naught. So when your velocity is u naught you are here. So for a simple case like when your p is 0, for p is 0 your profile looks like very simple, because p is 0, this term is gone, you only end up with 1 times y over b. 1 times y over b would be y over b. So velocity profile would be, velocity ratio would be very simple, this dimensionless distance y over b, or velocity would be u times this dimensionless distance. And how the profile looks like, because this is 0 velocity and this is u naught, so you have a linear velocity profile, because y is 0, multiply by 0 you get 0. When y equals to b, so you are here, b and b would be 1 multiplied by u naught, your velocity would be u naught. So your velocity is varying from 0 to u naught. So this layer would be somewhat lesser than u naught, lesser than this layer, and so on. This velocity would be 0. So you would have a typical velocity profile, and obviously where your pressure gradient term or your p term, which is a combination of p is 0 only because b cannot be 0, u cannot be 0, mu cannot be 0, 2 cannot be 0, only thing that is 0 is dava p by dava x. Then you have a straight line profile. Okay, if p have different values, you would have a different velocity profile. For example, in the previous case we see when p equals to 1, p equals to 1 means the whole thing is 1, then you have this typical velocity profile. So this layer would be moving with this velocity, and then velocity is decreasing but not linearly, non-linear. Your velocity would be this, your velocity would be this, your velocity would be this, and if p is 2 your velocity profile looks like this. If p is 3, it means more p means more pressure gradient. So more the pressure gradient, higher the velocity in this region, and then the lower the velocity, because this velocity is this plate is stationary, so the velocity is 0 here. So you get this typical velocity distribution. Okay, let's see if p comes out to be -1. So your velocity is this, your velocity is this, 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 and this. And p equals to -2, also your velocity is this. But p equals to -2, you see there is a trip point. It means here the velocity is in the down towards a positive x, but this part would be in the negative x. So this is what is called backflow, because at this point this is called a tripping point. You see the velocity is positive, positive, positive. Here velocity has changed its direction. Here it is in the positive x direction, here it is in the negative x direction. So this would be called as a backflow. So it means some layers of the fluid would be moving in this direction and the bottom layers would be moving in the opposite direction if you choose p equals to -2 or -3. So by just substituting different numerical values, you can end up with certain graph as well. Okay, in the last, actually, this is a very important application. It is actually journal bearing. Journal bearing means the shaft, which you call it a journal, that is a rotating part, and the housing is a stationary part. So this stationary part is act as a fixed plate, and this layer of the shaft, which is in rotation, would be called as a moving plate, and between that there is a lubricant there. So we call it the rotating shaft would be your journal, which is a rotating part, and the housing is a stationary part. And if you look at closely, you can see this top plate is moving with the velocity is r times omega. Omega is the angular speed of the shaft, and r naught is the radius. So this layer would be moving with the speed r naught omega. And here the velocity would be 0 because the plate is stationary. So here the velocity is 0 because the plate is stationary, and if this plate is moving with a certain speed, angular speed omega, its tangential velocity would be r times omega. So that layer would be moving. So we can think of such problems can be resolved where this lubricant, the distribution of the velocity we can work out. So this is an important application of the Couette flow, in which one of the plate is fixed and one of the plate is moving, even though it is moving in rotation. But if you just make a small section, it would be considered as a horizontal section. So we can have an idea at different layers of the lubricant what will be their velocity. So this important information we get it by solving this Navier Stokes equation. So this is where we end today's lecture.